Hi everyone, welcome back. So today I thought what I'll do is I will do an example of using some of the techniques we've developed in the past few lectures, which are integral equation approaches and physical optics and geometrical optics to design a parabolic reflector antenna. Okay, so we're choosing parabolic reflector as sort of an example of using these techniques. And also because we want to talk about how actually these antennas are designed, because we did not discuss parabolic or reflector antennas when we discussed antennas in the past in this course, right? So now we have the tools to kind of analyze them. So this is a nice place to talk about parabolic antennas. So what we'll do is we'll spend a few minutes going over some of the concepts behind reflector antennas. And then once we have those concepts done, then we'll open HFSS and and then design a parabolic reflector there. Okay. So the first concept is that of a phase center. Okay. So every antenna has something called a phase center. So what is this phase center, right? So we know that in the far field of an antenna, let's say any antenna, this can be, and if you're far enough away from this, then we know that the radiation field is approximately spherical, right? So what that means is that the phase propagates as e to the ikr over 4 pi r. That's the leading term, right? So because this e to the ikr term represents a spherical phase front, that sphere has some center, right? If you have a sphere, the sphere is, with respect to some coordinate system center, right? So this has some center here, okay? So on a sphere centered at this point here, the phase is constant on the surface of that sphere. And if you move the sphere to a different location, let's say if you pick a sphere here that is centered at this point, then the phase over that sphere will not be constant, right? So that point is called a phase center. Okay, so we often need to find this phase center because then we can use approximations like geometrical optics to design these reflectors, right? Because we saw that when you're kind of at very high frequencies, that's the reason it's called optics, geometrical optics, because when you have very high frequencies, then you can approximate essentially rays going out. And we haven't really seen what rays are yet. We'll see them later. But basically, these rays come out from this phase center. And they're all equidistant, have the same length, right, at the surface of this sphere. And that will make a little bit more sense later in the next couple of lectures when we do plane waves. But essentially, that's what this phase center is representing. So these rays coming out from that point. Okay, so a parabolic reflector, discuss that next. Then it has two parts. It has a feed antenna, and a reflector. Okay, parabolic reflector, something like that. And we kind of know that if you have a reflector, if you have a parabola, then draw it in a different color. If you have a parabola, then that parabola has a focus, right? So this is the focus. Okay, so any ray coming out of this focus, hits this parabola and then goes out parallelly to the axis of the parabola, right? So that's one of the properties of a parabola. We've seen that before. Okay. So we write this. So this point here is the focus. And we want to place the focus on the phase center of the feed on the feed horn, right? Only then you can approximate these rays as coming out from this point, and then they all come out parallelly. Okay, so that's the ray optics model. Of course, you can also model it with geometric or physical optics and integral equations, which is what we'll see today. Okay, but since we know that this is a very smooth surface and the frequency is considered to be very large, which means the wavelength is much, much smaller than the radius of curvature of the surface, then you can essentially use geometrical optics and simplify the analysis quite a bit. Okay, so the equations of this parabola in terms of xyz are, so what we want to do is we want to say, okay, this is the z-axis. I'll call this as the z-axis, and this is the rho axis, right? So this is cylindrical coordinates, just because we have cylindrical symmetry in this problem. Okay, so in this coordinate system, I'll place the origin here at this vertex, 0, 0, 0, out here. So when the origin is out there, then what you want is to define this surface. This surface, we need to write z as a function of rho, right? Which means that as you move away from this point, the value of z changes, right? So this point, the value of z is that, this point, the value of z is there, and so on. So as we move in this direction, we want to know how much we want to move in this direction, right? So that gives you z in terms of rho. And you can easily show that from the definition of a parabola, it's rho square over 4f, okay? Where f is the length of the focus, or the focal length. So this is your f, okay? All right, and of course we have x and y because it's just cylindrical coordinates. X is rho cosine phi, y is rho sine phi. So we need these equations when we want to draw this in HFSS, and that's why I'm writing them down here. Okay, so there are some parameters for a parabolic reflector antenna, or pretty much any reflector antenna, that we want to define. Okay, so the first thing is the physical aperture. AP, and that's nothing but pi d squared over 4. Okay, so let me actually just move these out here, where d is this diameter. So this diameter is called d. Okay, so it's not the exact area. We're assuming the area is sort of flattened out because there's some curvature. The actual surface area of the parabola would be larger than that, but we ignore that part and we just say it's the area as if this parabola was flat, right? Okay, so that's just pi r square basically. And then there's another effective aperture for every antenna, which we've defined earlier. And we can show using reciprocity. That this is related to the gain of the antenna as lambda square g over 4 pi. Right? So that's just a general concept in antennas. And what we want to define now is what is called aperture efficiency. Okay, eta, which is AE over AP. It's the ratio of the effective aperture to the physical aperture. Okay? All right. So based on these, we can figure out, what this actually, all this, why is all this so important, right? So the gain is written as 4 pi AE over lambda square, which is the same thing as this equation here, right? This equation here. So this I can now write as eta times 4 pi AP over lambda square. Okay, where eta is your aperture efficiency. All right, so what is this saying? So this is saying if I have a parabolic reflector antenna, or any kind of reflector antenna that has some physical size given by AP, and I know the wavelength, then I should be able to predict the gain in terms of this quantity aperture efficiency. So once you've determined this, the rest of it is all based on physical parameters. And so what is this aperture efficiency? Okay. So it has many factors. The simplest way to think about it is that if I had a current distribution, let's say I had some kind of a disk, right? So I'm just drawing the cross section of this disk. And the current distribution on this disk was a step function. It is 0 everywhere. And then it becomes 1 or large here. And then it becomes 0 everywhere else. Right, so if this was the case, then my gain would just be 4 pi AP over lambda square, right? Because we saw that effective aperture is essentially the aperture of the current distribution, and the current distribution is uniform everywhere, and that's just the physical aperture of this disk, right? But in reality, we know that when you illuminate a reflector, even if it's just a disk, so we go back, and if I draw this disk now, again, so this is the cross section of the disk, and I place a horn feed here, like that, then I know the illumination is not going to be uniform. The illumination will be something like this, right? So this is essentially the illumination of the current distribution, right? Because the field coming here has a shorter path length than this field that comes out all the way at the edges, right? So it's stronger here and then slowly decays and becomes weaker and weaker as you go further away. And some of this field also doesn't hit the reflector, can go beyond, right? So to capture the effect of the illumination, the fact that it's not uniform, we need to introduce an efficiency. And that's essentially what this efficiency parameter is capturing. It's saying how much do I deviate from this ideal current distribution of a step function. Okay. Okay, so it has many components. So eta can be broken down in different ways, but most common one is an illumination efficiency, a spillover efficiency, has a phase efficiency, polarization efficiency, blocking efficiency, and surface efficiency. So we'll see what these mean. So illumination efficiency essentially is saying, how close is it to being fully illuminated like this, right? Which means what? Which means that if I have a beam pattern that has very, maybe I should talk about what a taper is first. So we'll discuss that first. Okay, edge taper. Edge taper. So you can say it's the power at the edge of your reflector versus center of the reflector. Okay, so typically numbers for edge taper are like maybe it's -3 dB, which means it's 3 dB taper, or -6 dB, which means it's a 6 dB taper, right? Or -10 dB, which means the power at the edge is 10 dB lower than the power at the center. Okay, power density rather, and so on, right? So of course, if you have a step distribution like this, then the edge taper is 0 dB, right? Whatever power is here, you have the same power out there, same power density. So when you have that case, then the illumination efficiency is 1. Okay. But when you don't have that, let's say you have some power here and the power here is a bit lower, then the illumination efficiency is less than 1. Okay. But of course, you can never make a horn antenna that has radiation such that this point and this point receive the same illumination as this point, and it goes to 0 just beyond that, right? So you can either make it something like this, the illumination where there is very low taper at the edges, and there is no spillover. So no power is being spilled, is being lost to the spillover, which is what contributes to the spillover efficiency, and how much power is actually not hitting the reflector, right? Or you can make it very broad, like that, in which case the spillover efficiency will be very would be low. But since the taper is also very low, close to maybe -1 or -2 dB, then this illumination efficiency would be high. So there is a trade-off between these two. Since you can never make a horn antenna that produces perfect rectangular or step function distribution in the current distribution, you will always compromise between the illumination efficiency and the spillover efficiency. Okay? So in words, what does that mean? If the taper is high, spillover efficiency is bad, poor, which means there's a lot of spillover, but illumination efficiency is high. Okay? So taper high meaning 0 dB is higher than -10 dB, right? So if the taper is -10 dB, it's low. Taper is -3 dB, it's high. Okay? If you actually go ahead and plot this, so I'm just sketching the plot here. It's a rough plot. Right, so on this side, I'm plotting the efficiency, different kinds. And here I'm plotting the taper. Okay, so maximum taper, let's say, is 0. And then -5, so this is -10, -15, -20, and so on. Then your spillover efficiency will do something like this. Eta spill. Right? Because when the taper is low, there's no spillover, so it reaches 1 asymptotically. And illumination efficiency does the opposite. Illumination efficiency will do something like this. This is your illumination efficiency. Okay, so if you actually take the product of the two, you will see that there is kind of a maximum, something like that. Yeah, I haven't really drawn this correctly, but this maximum should be, it really depends on the kind of distribution. So we've kind of simplified something very complicated, which is the distribution of current into just a single factor or two factors of illumination and spill, right? Because you're only looking at the edge values here and determining what the taper is. But you can have the same taper, but a very different distribution in the middle too, right? So it really depends on what exactly is the distribution of your radiation source. Is it like a cosine distribution? Is it a Gaussian? Is it squared cosine? Right? What kind of radiation pattern you have? So you can't say that for all antennas this peak happens, for all feeds this peak happens at -10 or -6 or something like that, right? So it really depends. So I want to actually redraw this a little bit so that I'm not off. So let me also redraw this one. So maybe the maximum is something like that, right? Okay, so this is the total eta. And I'm saying, okay, this peak maybe happens at around -10, but it can happen at different values depending on the actual distribution of your feed. Okay, let's say this is -20. Okay, so what are the other factors that were in here? Right, eta phase is because you don't have an exact spherical phase front in reality, right? You have some aberration in the phase. Depending on how far you are from your feed, it's not like, oh, if you're just 2D square over lambda, then your phase is perfectly spherical, right? That 2D square over lambda is kind of somewhat an arbitrary line. It doesn't mean that beyond that, everything is spherical and below that, everything is not spherical, right? There's a slow transition. And those 1 over r square, 1 over r cube terms do contribute even at far field, right? So they do disturb the phase a little bit, and that can change this factor. Polarization is, if you have If you want vertical polarization, but there is some cross-pole component when you go far away from here and here, then although power density may be good, but what is reflected out is of an unwanted polarization. Right? And that can reduce the actual power received by some antenna, because in the far field, you want to have a certain desired polarization. And there is a blocking efficiency, which is the amount of power that is blocked by the feed itself. How much is reflected off? Some of it is blocked by the feed. Some of it is blocked by the support structure of the feed. So you could have like supporting beams like that, or a supporting structure like that. That can block some radiation. And then there is eta surface, which is the accuracy with which the surface was machined. Right? So there are some imperfections in the surface geometry that can add phase aberrations. If it's not, they can be high frequency, for example, like roughness, right? Or they can be low frequency, which is like bending of the surface. And maybe it's like a little bit warped, and it's not ideal. And those two have slightly different contributions to the far field. Okay, so that can come in here. So these ones are essentially, or at least these ones, I would even say these ones are more dependent on manufacturing accuracy, right? Whereas these ones are dependent on the feed. Okay. All right. So in reality, we mostly care about optimizing this product. And in this product, we try to just make sure that manufacturing tolerances are as tight as possible based on the budget that you have and the manufacturing technology that you have access to. Okay, so with all that in mind, a good number to keep track of is that efficiency is around 0.55 or so when the taper is, edge taper is minus 10 dB. Okay, so this is the typical optimum, or it's close to the optimum efficiency you can get. Okay, so in reality, I mean, if you just take the product of illumination efficiency and spillover, this should be around 0.75 or so. But because of the other factors in there, this can be brought down to around 0.55. Okay. All right, so now we'll do the design example and then take that to HFSS and see how we can simulate it using integral equation, which is method of moments, physical optics, and geometrical optics. Okay. So design example. So let's say I want, I have minus 10 dB taper. That's what I want. And that's around 80 degrees. So this is the beam width of the Potter horn that we designed in one of the earlier labs. Right, so that one has a 10 dB. If you plot the radiation pattern, you plot the directivity pattern. Right, if you look at, let's say this is the maximum normalized directivity, 0 dB, and you go down to minus 10 dB, then this beam width is 80 degrees. So we want to have minus 10 dB taper, so we have to work with this. So we need to make sure that the angles that cover this range are the angles that illuminate the reflector. Okay. So that's what you have. You've given this feed and you want to design a reflector now with a gain of 40 dB. That's the total gain that we want. Okay. An important factor is what is called the F over D ratio. Okay, so this is an important ratio even beyond reflector antennas. Basically for any kind of focusing element, like even lenses, this is an important ratio. So we want to know what this ratio is. Okay. So what do we have? We have a beam that has a beam width of about 80 degrees. And we want to find out based on that, what's the F over D? Right, so I have my F, which is this. This is the source of my horn. And then this is my D, which is the diameter of my reflector. Right, so from this, very simply, you can look at the geometry and show that tan theta minus 10 dB divided by 2, which is this angle, is equal to D over 2F. Okay, which means the F over D ratio turns out to be 0.5 596. So that's what we need to use. Okay, so now we want to go to gain. Right, I know gain over efficiency is nothing but 4 pi over lambda square times the aperture, physical aperture, which is pi d square over 4. So this whole thing turns out to be pi d over lambda whole square. So that gives me a value for d, which is lambda over pi square root of g over eta. Okay, so once I have this d based on the wavelength of my choice, gain that I like, the efficiency that I have, I can get d, and then from d, f over d, I can get f. And that completes the design. Right, so let's do that. So let's say I'm operating at 10 gigahertz. That's what we've been doing so far. Then d over lambda, but it doesn't have to be. I can just do it in terms of lambda. Is 1 over pi, and we want a gain of 40 dB, which is 10 to the 4, divided by 0.55. That's the typical efficiency for minus 10 dB taper. That's what we said, right? So this comes out to about 42.9. Okay, which means that at 10 gigahertz, we have lambda equal to 3 centimeters minus 2, plus d turns out to be 1.29 meters, and f turns out to be 0.77 meters. Okay, so now we have a design example because we have the dimensions and we also have the equations, which are these guys up here, right? These guys. From that, we can easily draw this in HFSS and then simulate it and see whether we get 40 dB or not. Okay. All right, so let's jump into HFSS next and do the design. And then we'll see how to use the different solvers in HFSS to do that. Okay, so let's do a demo of actually designing this parabolic reflector. So I'm starting from what we did a couple of lectures ago in the lab, where we designed this powder horn, and I want to use the same kind of design. So let's do that. So I'm actually name this to 16L. Today we'll do IE, PO, and GO. Okay. We don't need this other design, so I'm just going to delete that. And we'll work with this. Okay, so we'll change a few things. Go to solution type, make it HFSS with hybrid and raise. Hit OK. We'll delete this airbox. And we'll create a new airbox with this FEBI boundary, FEBI, which stands for finite element boundary integral. You can look at what this is maybe once we do finite element, but essentially it's a combination of finite element and method of moments. Okay, so that's what that is. I won't say too much about that here, but you're welcome to look at what that is. Okay, so we have our radiation box now, our FEBI box. And the next thing we want to do is actually find where the phase center of this antenna is, right? So let's do that. So in order to do that, I need to make a coordinate system. Okay, so first I will move my whole antenna. Edit, arrange, move, such that the aperture is at the origin. You don't need to do this, but I'm doing it anyways. Okay. So I just want to check that that's the case. Measure position. Right, so the Z position is 0. Okay, that's good. Now I'll make a new coordinate system. Go to modular coordinate system, create relative offset. And I'll say this is Z, BC, Z offset. Okay. All right, so if you don't get this option, you should hit F4 and it'll take you to this option. And you can go to my website and look at different HFSS hotkeys if you haven't seen that before. So I'll set this to some value, say 5 millimeters. So now you can see that this moves and I change this value, right? Okay, I want to create a new far field setup in that coordinate system, which is this one. And actually rename it. So I'll call this phase center coordinate system. Okay, far field setup, infinite sphere, and then we'll select the phase center coordinate system. And I'll go from 0 to 180 and minus 40 to 40. So I'm only going from minus 40 to 40 because that's the radiation that is going to illuminate the reflector based on our hand calculation, right? Because that's the beam width, the 10 dB beam width. Okay, that's done. Analysis can stay the same, 10 gigahertz. These options are all fine. What I can do is go ahead and run the simulation. Okay, so it should take a couple of minutes and then we'll come back and continue from there. Okay, so simulation is done. We can go ahead and look at the results. So I'll say I want to look at the 3D polar plot. Last adaptive over the sphere that I define, the electric field, and the Y polarization of this electric field. And the reason I care about the Y polarization is we need to set this such that the horn itself has Y polarization, right? So then I can keep that fixed over 3D space. If I choose R theta or R phi, E theta or E phi, then that depends on which plane you're in. This will be the copole or this will be the copole. Whereas if I choose this will always be the copole for all planes. Again, when you care about angle, when you're looking at the phase, you need to make sure that it's phase of the main copole radiation, right? Because phase of cross pole is kind of meaningless because there is hardly any cross pole, right? Because the magnitude is basically zero. Okay, so you can choose this or this. I typically go with this definition of the polarization, which is Ludwig's third definition, I guess. You can read up what that is, but it's just a different way of defining polarization based on which coordinate system you choose. Not coordinate system, based on the way it's defined. I don't want to say too much about that, but I'll use that for now. Okay, hit new report, and this does not look right. The reason it does not look right is because the feed, this is always something to keep in mind, has two polarizations, right? One is this X polarization, that's where the electric field is. The other one is Y. So we need to actually select Y as the source, which is this one. So I'll send power to the Y port, not to the X port. The Y mode and not to the X mode. Okay, if you don't know what that means, when we discuss waveguides, you'll see that, but just set that to be correct that way. Okay, and this is actually correct. Okay, so now what I want to do is essentially, you see here the variation is about 14 degrees between the maximum and minimum phase over the sphere. And so 14 degrees is pretty good, but essentially we will change this and see that that changes. It should not have to rerun the simulation and it's doing this. So maybe I need to choose a different name. Let's say PCZ. I think it's better to create the coordinate system after the simulation is done. Then it treats it as a post-simulation variable. And then you can change it after the simulation, and then it doesn't have to re-simulate. Okay, so let's try that. So I've created this new coordinate system, and you see that, okay, this has changed without having to re-simulate, right? Because it's just a post-processing variable, which calculates this phase. Okay, so now you see that the variation is again around 14 degrees or so. But we'll see how to do this more rigorously. Okay, that's what we'll do now. So to do that, I'll set up an optimizer and a parametric sweep. And I'm going to set the parametric sweep over PCZ to go from 0 to 10. And with a step size of 0.5 millimeters, hit add. Go to calculation, setup calculation, far fields over the infinite sphere we just defined. Select the same variable and hit range function. And here we're saying what is the peak to peak, calculate the peak to peak value of this variable, which is the phase of the far field, E field, over minus 40 to 40 degrees. Okay, close that, hit OK. But this is only going to calculate it over the H-plane, right? Which is phi equal to 0 degrees. Hit add calculation, hit done, hit OK. And now you can right click here and say analyze. So now since the phase center is a post-processing variable, it should not have to calculate it again and again. So you see it's very fast. Okay, so once it's done, hit view analysis results. And we see that the minimum variation in the H-plane is when the phase center is at the aperture. Okay, and of course, you can go to minus values and you'll see that that will still be 0. Okay, you can do that if you like. So let's say edit, go to -2, update, and then rerun that. Okay, that was very fast. Yeah, so at 0, which means the phase center in this cut is exactly at 0. How about the E-plane? So we want to change that, right? So I will edit this and then say phi equal to 90 degrees. Hit OK, hit OK. And then analyze this again. Okay, so let's go back, view the results. So now you see that the minimum is around 5 millimeters, right? So for the E-plane, the phase center is slightly off the aperture, 5 millimeters off, whereas for the H-plane, the phase center is at the aperture. And that's not that uncommon that in two different cuts, the phase center moves because the phase front is not exactly spherical. It is somewhat elliptical, right? So it's like in one cut, it has a slightly different radius slightly different radius compared to the other cut. No, not slightly different radius, slightly different origin, I guess. Okay, so maybe it's a little bit easier to visualize in this case. So you see that when the phase center is 5 millimeters in E plane, which is this plane, right, there is no variation. Whereas in the other plane, there's maximum variation. Whereas if I make this 0, then we see that now in H plane, which is in this plane, there's maximum variation. It's going up and coming down. And in E plane, there's very little. Right? Of course, at the end of the day, it doesn't matter that much because this is only 14 degrees of variation, which is not much. But if you really want to be very optimize it, I would say place it somewhere in the middle, where in one case, in the E plane, there is some variation, and in H plane also there is some variation, but both cases the variation is somewhat reasonable. It's not too much. Okay, so this looks kind of like a saddle, right? And that's what we'll go with. Okay, so I'll say that the phase center is right there. It's important to keep in mind that you should be a little bit careful about, selecting the phase of different cuts and optimizing over them, because you need to make sure that you're choosing the right polarization. And you can check that by looking at the dB value of these plots. Okay, so when you plot your polarization, it should be a nice beam like that. Okay, so if it's not a beam like that, then you've done something wrong. Okay, so we know where the phase center is. Now we can go ahead and design our reflector. So let's do that. Okay, so I'll create a new design. Call this Parabolic. We'll do it integral equation first. Okay, go back to solution type, make it HFSS with hybrids and arrays, network and model. Okay, and now we want to draw this parabola, right? So how do you actually draw this? And there are many ways to do it. What we will use is we'll use this equation-based surface. Okay. So you have to essentially define the x, y, and z coordinates of the surface in terms of a parameter, in terms of two parameters u and v, right? Which is how surfaces are defined. So our u and v parameters are phi, rho and phi, because it's a function of rho and phi. So it would be minus u underscore u times cosine underscore v, that's x, underscore u times sine underscore v, that's y, and z is underscore u times underscore u, which is rho square, right, divided by 4 times the focal length. Okay, and then u starts from 0 all the way up to dO2, because u is nothing but rho. V starts from 0 all the way up to 2 pi. Yeah, we need to define what f and d are, and that's what we calculated earlier, which is that f was 0.77 meters and d was 1.29 meters. Okay, so that's our reflector. Nice. Okay, so to extract fields from this feed and then put it into that, we need to export this as a 3D component. So select all in object selection mode, say draw, 3D component library, create 3D component. Hit OK. And then you can save it here as horn param. Go in here. And now you want to import it here. So in order to import it here, we need to create a coordinate system for this one, right? So let's do that. I'll say modular coordinate system, create relative both. Just hit OK for now. Go in here, and then we'll change it now here. So the origin of this coordinate system is with respect to the global coordinate system, 0, 0, minus PC, which is the phase center. And the value of PC is 2.5 millimeters. Where is the global coordinate system? It's there. Why is this so far away? Okay, there we go. I think there is a mistake somewhere. Equation-based curve. 0 to 2 over T or D over 2 should be 645 millimeters. Why is it 645 micrometers? That's not correct. Value of T. D is, maybe like it does 1.90 millimeters. 770 millimeters. Okay, that's correct. Okay, so okay, and then this one has to be F. So we have, let's just say this is the focal length. Okay. So F length, no, we selected F, right? We called it F already, so I shouldn't rename it. Let's just say F, okay. So now we are at F, and we need to change this one's orientation. So I'll say axis position, and change the direction of Y. Well, it's pointing in that direction, okay? So essentially, I want to import my model into this coordinate system. So I'll say modeler, import, sorry, no, draw, 3D component, browse, and then say horn param. The target coordinate system is the relative coordinate system. And now this has been imported here, okay? And you can see that since we exported it when we selected this coordinate system, which is the face center coordinate system, it already has the gap. So it imported with respect to that coordinate system, which is what we wanted, right? So the focus is still here, and then this extra distance is the face center. Okay, so the face center is in fact here. Okay, so we've imported that now. And we want to use, so we can't really solve this with finite element, because if you do that, if you try to create a radiation box that's this big, it would be way too big for finite element. So that's the reason that we want to use now integral equation, which is method of moments, physical optics or geometrical optics, right? So to do that, select object, right click here, assign boundary, perfect E, hit OK. And then assign hybrid, select again, assign hybrid, IE region. So that's the method of moment solver. Okay, integral equation, hit IE, hit OK. Now when you open this, you'll see that there is a boundary, perfect E, excitation, which is the one down here. Let's make this such that it's this way. And there's also this hybrid region, which is the I region. So this is going to solve for the currents on this surface and then radiate from that. Again, that's pretty much all you need. You don't need a radiation box now. Of course, you need to set up a solution. So we'll solve at 10 gigahertz, 20 passes, 0.01, 2 converged passes. Okay. And I don't want the frequency range, so I'll delete this. And now it's ready to solve. Okay, so once this solves, I'll come back and we'll look at the results. Okay, simulation is done. That took a few minutes. So let's take a look at the results. We can set up a far field. So let's just look at the two cuts, 0 to 90 and minus 40 to 40. I mean, you can look at the full thing, that doesn't matter. So just for simplicity right now. Far field results, let's just do a rectangular plot, and we want to look at the total gain at 10 gigahertz for all values of field. Okay. See what that looks like. So of course it takes a few seconds because it's calculating the fields. I want to have a slightly better resolution. It's 2 minus 0.5. Okay, so that's what the beam pattern looks like. I can add a maximum. You see it's close to 40 dB, right? About 41 dB or so. So it agrees with what we started with. Our back of the envelope kind of hand calculation, right? Where we approximated eta to be 0.55 or so. To it's a little bit higher, probably 0.6 or so for minus 10 dB taper. Okay, so this is using IE and it's a little bit slow. What we want to do is to speed it up. So now we'll use physical optics. Okay, and we looked at these two in the lecture already. So in order to do that, all I need to do is change the surface here and make this into a PO region. Okay. Or when you're assigning it, you can assign it directly from here, assign hybrid PO. But since we already did that, now it has physical optics enabled. Okay, so we'll simulate this, and this should be much faster. So once that's done, we can continue. Okay, PO was done. We look at the results, very similar. So I increased the resolution to 0.2 degrees for both of them. And we can compare the two, and you see that they're very similar, right? This one and this one. I mean, of course, you can even change the scaling and so on, such that it's fixed. Minus 40. Right, so very similar. You can also copy the data and then plot it here. And you see that they're almost the same, right? Almost no difference. Okay, so that's great. That's great news, which means that a full wave solver in physical optics, which is a huge approximation, works pretty well when the edge taper is low, right? So the edge taper needs to be low so that there's no edge diffraction that's significant. And the curvature has to be have a large radius of curvature. The last option is SBR plus, which we'll also quickly do and see what it looks like. So SBR plus is kind of a advanced version of geometrical optics. Okay, so that was the last option there. Go back here and set it to SBR plus. Okay, and then we can simulate this. That's true. We need to change a few things when you do SBR plus. You need to change the domain of radiation. So I need to redo this. So delete this, add advanced 10, 30. Yeah. Field observation domain needs to be set to infinite sphere. Okay. And you can change these values of the number of rays per wavelength, the maximum number of bounces. Here we only have one bounce, so it doesn't matter. And you can add extra wedge correction factors. Right? We discussed a little bit, not discussed, we really just very high level discussed what PTD is. Creeping wave we haven't really discussed yet, but you can add these correction factors if you like. And now we'll just leave them. Okay, and then we can delete this. And now we can run the simulation and see what happens. Okay, and compare them with the other two cases. So in the lecture, we looked at IE, method of moments, physical optics, and geometrical optics, and derived one from the other. GO really can be derived from scratch as well. There's something called the iconal equation that you can derive, and then from that, establish geometrical optics. We haven't really done that approach. That would be more like an optics class. Maybe we can do it. We might do it later or in a separate lecture, a supplementary lecture. But the derivation that we did in class using stationary fades is a little bit simpler to understand once you understand physical optics and so on, right? So once this is done, so this should be much faster compared to even the other two, right? Because it's just a few rays. So maybe I'll pause until it completes and then we'll continue from there. Okay, SBR plus simulation is done. That's what that looks like. And once again, very similar to physical optics, right? But basically almost exactly the same. Because once again, it's a very smooth surface and most of the radiation at any given point is dominated by that specular component. Okay, so that was just a demo of using 3 different techniques that we discussed in class to design a parabolic reflector. We also looked at phase center, what it means, and how do you actually simulate it using HFSS. There are other ways to simulate it as well, but we looked at one example here. Okay, so hopefully that was interesting. So we learned basically new ways and different solvers that we haven't discussed before that HFSS offers. And of course, other softwares maybe also offer similar tools, but it's nice that we have all of this in one place, right? Okay, so hopefully that was interesting. And if you have any questions, you can leave them in the comments below. If not, I'll see you in the next one. Thank you.